Namaskar friends. Welcome to MedDwise Circle Educational Video Lecture Series. In this video lecture series, we are going to discuss the fundamentals of clinical chemistry test in a pathology lab. This is intended to be viewed by freshly newcomers in IVD industry who have recently completed their education, or maybe experienced people who are working in IVD industry for a few years and want to refresh the basics again, or maybe our laboratory technician brothers and sisters who are doing the pathology test themselves. This video lecture series is made in collaboration with Anamol Laboratories Private Limited. So allow me to share my screen. I hope everyone can see the screen. So in this video series, we are going to talk about the fundamentals of clinical chemistry test, which is majorly used in the pathology lab. So this video series focuses on 4 different modules, out of which the first module only covers about the basics of photometry. In this, we are going to cover various topics. For example, such as what is wavelength, what are complementary colors, what is Beer-Lambert's law, what are the components of a colorimeter, and what is the difference between colorimeter and a spectrophotometer. But today, in this video, we are only going to cover about 2 topics. The first 2, which is what is wavelength and what are complementary colors. So let's get started. We will start with the basics. What is photometry? Friends, you can see that in our IVD industry, we use these terminologies very common. What is wavelength? 510 nanometer, 546 nanometers, so on and so forth. But do we realize that everything in clinical chemistry, whatever we do, it is initially started with the concept of understanding of the light. What exactly is light? So friends, we know that light, when it travels from point A to point B, it does not travel in a straight line. It travels in the form of a wave, as you can see in the image. So here we can see that this is our point A and this is our point B. So when the light travels from point A to point B, it travels in the form of a wave. Now, if you see from the starting or the center line, there is a portion of the light which is on the upper side of the center line. And there is a portion of the light which is on the lower side of the center line. The upper side of the center line is called as crest, C-R-E-S-T. And the lower side of the wave is called as trough, T-R-O-U-G-H. Now we know that since the light travels in the form of a wave, the distance between 2 consecutive crests or the distance between 2 consecutive trough is measured in nanometers. This distance is nothing but it is called as wavelength. So whenever we use the terminology wavelength, it is nothing but it is the distance between 2 consecutive crests or 2 consecutive trough. Here the word consecutive is very important. So this is measured in terms of nanometers. It is denoted in the Greek letter which is called as lambda. So you may have very much encountered in your day-to-day life. There is something called as lambda max, which is maximum wavelength, and so on and so forth. Therefore, wavelength is always signified by the letter lambda. Now, based on this fact, the entire spectrum of light is divided into 3 distinctive parts. The first part, or the first 1/3 part of the spectrum, is called as UV spectrum, or it is called as ultraviolet spectrum. The middle part is called as visible spectrum. And the next to visible spectrum, this part is called as IR or infrared spectrum. Visible spectrum is called as visible spectrum because this is the wavelength of light which is visible to human eyes. This is possible because this particular wavelength of light is colored in nature. You can see that it starts with 400 nanometers and it goes all the way up to 700 nanometers. And there are basically 7 distinct colors that we see from 400 to 700 nanometers. This color are signified as Vibgyor, which is violet, indigo, blue, green, yellow, orange, and red. Precisely, these are also the colors that we see in a rainbow. The light which is less than 400 nanometers is called as ultraviolet light. And the light which is more than 700 nanometer is called as infrared light or IR light. Hence the terminology UV range, visible range, and IR range. Now, why this knowledge is important to us? Because technically, if we see, what do we do in a pathology lab? In a pathology lab, just imagine that we have to find out the concentration of glucose in a patient sample. Now, what we will do in a pathology lab is, we will take the reagent and we will add the reagent in something called as a test tube. I hope you can see this. There is a solution in the test tube. Now, just imagine that in this test tube, we have added the glucose reagent, and in that we have added the patient sample, which is human serum. Now, whenever there is a reaction, you can see that the color of the reaction is not transparent. It is of a particular color. Now, this color solution, when we expose this colored solution in the path of the light, it will absorb some amount of light. Therefore, we need to understand the concept of light. Now, we have to understand something which is called as complementary colors. What exactly is complementary color? So friends, I did show you the example of a test tube. As you can see, in this test tube, the liquid which is there is slightly violet in color. Now, think about it. If the solution is violet in color, and when we pass the violet light from this solution, will it absorb the light? Technically, the answer is no. The reason is because if this solution is violet in color, it will absorb all the other light except violet color. That is why, since it is not absorbing the violet color, it is allowing the violet color to get transmitted. Therefore, the color of this solution is violet. Now, this concept is called as complementary color. Complementary color is nothing but it is the color which is directly positioned to the solution color in something called as a color wheel. Here you can see we have described the color wheel. Now, color wheel is nothing but, say for example, in this example, the solution of the color is violet. So we have to pass exactly opposite color, which means yellow color, through this solution. Which means that if this solution is kept in the path of a yellow colored light, then it will absorb the maximum light. This concept is called as complementary color. So here you can see that it depends on the reaction mixture, what color of the light we have to throw on the solution. Say for example, if the solution color is green, then we cannot pass the green light through the solution. We have to pass the opposite color, which is the red color, through the solution, red colored light through the solution. If the colored solution is blue, then we have to pass orange light through blue colored solution. The reason is because that blue color and orange color are complementary to each other. Therefore, a blue colored solution will maximum absorb orange color light. So here we have given some common examples of primary colored pairs. Red pairs with green color, blue pairs with orange color, and yellow pairs with purple color. So therefore, it is important to understand that if I have to find out what is the concentration of glucose in this particular colored solution, I have to use the yellow light wavelength. And I have to pass yellow light through this solution so that the solution will absorb maximum amount of light. We will go more into details in our upcoming lectures of how we can find the concentration. But here there are two more concepts which are important to understand. These concepts are called as absorbance maxima and absorbance optima. Now, what exactly is the meaning of absorbance maxima and absorbance optima? Now, here it is important to understand that when the colored solution is purple, we understood that we have to throw orange light through this solution. But what exactly precisely the wavelength of the light we have to pass through the solution? How will we find this out? So here, what we will do is we will do an experiment. In this experiment, we will say that let us start from, let's say hypothetically, let us start from 600 nanometer and let us go all the way up to 650 nanometer. Just this is to give you an example. So when we pass 600 nanometer of light through this particular solution, then the solution will not absorb any light. Therefore, the absorbance which we are plotting on the y-axis will show zero absorbance. But as and when we start increasing the wavelength from 600 to 601, 602, and so on and so forth, we will see that the absorbance has started to increase. That means now this solution is starting to absorb the light. We will see that at a particular wavelength, the absorbance by the solution is maximum, as which is shown in this graph. There is a point which is called as lambda max. See, here is the point. Now, in this point, at this particular wavelength, the absorbance which is shown by the colored solution is the highest. Beyond this point, even if we increase the wavelength, the colored solution will still not absorb the light. On the contrary, it will reduce the absorbance of the light. Therefore, this particular wavelength of light is called as lambda max, which means that it is the wavelength at which the solution will absorb maximum amount of light. Let's say hypothetically, just for example, this wavelength is 625 nanometer, just to give you an example. So 625 nanometer is called as lambda max. But there is a different concept which is called as absorbance optima. Now, what is absorbance optima? To understand this, let us understand that in this example, when I added the solution of glucose and when I added the patient sample, human serum sample, now we have to understand that in human serum, it does not has only glucose molecule. Human serum will have multiple other molecules also. Like for example, it will have lipid molecules, it will have bilirubin molecules, it will have hemoglobin molecules. Now, these molecules also absorb the light at 625 nanometers. So what happens is, in turn, the total absorbance, what the solution absorbs, is consistent of the absorbance by the glucose molecule and also the absorbance of any other molecule other than glucose. But do we want to identify any other molecule other than glucose? The answer is no. We have to only identify what is the concentration of glucose. Therefore, what we will do is, we will not take the absorbance at 625 nanometer. What we will do is, we will take the absorbance slightly away from lambda max. Let's say hypothetically, this wavelength is 630 nanometers. So here we will take the absorbance at 630 nanometers. What exactly happens at 630 nanometers is that the absorbance of glucose, will the absorbance of glucose be compromised a little bit? Absolutely yes. The absorbance of glucose molecule will be slightly reduced. But the absorbance of any other molecule other than glucose, let's say for example hemoglobin. Hemoglobin molecule will show drastically reduced absorbance at 630 nanometers. Now this wavelength of 630 nanometer is called as absorbance optima. So absorbance optima is the wavelength at which the target analyte absorbance will be reduced only slightly, but the interfering substance absorbance will be reduced drastically. So we will not have interference from any of the interfering substances. So this is the concept of absorbance optima. Now, while doing any test, while the manufacturer is designing the IVD test kit, he decides whether do I have to take the absorbance of lambda max, which is the absorbance maxima, or do I have to take the absorbance of optima, which is absorbance optimum. This is very critical to understand that the target analyte will be estimated properly. Friends, I hope this video has been helpful for you. If you have any questions or if you have any kind of suggestions, please write down in the comment section. This will help us improve our future lecture series. Thank you very much, friends, and I hope to see you in the next video.